So let's see, the EMF, electromotive force of battery 1 here is 1.5 volts. The EMF of the other battery is 4 volts. Now I think the current is going to flow this way through R2. It'll have to return to the negative terminal, so I think it's going to flow down through R1. And it's possible that maybe this battery gets overcome by the other battery, or maybe battery 1 will actually send current here to the middle branch. So let's assume that this battery will contribute current into the junction, and so will the other battery. I'm going to call this one I3. This one can be I1 and I2. Now let me redraw that so that we can see it a little better. This is 4 volts and 1.5 volts. I'm saying that I think the current I3 will go to the right. I think I2 will go to the left. I think the current will go down through that resistor. Alright, those are my initial guesses. Now I want to start at a particular point in the loop and go all the way around the circuit. Now this red does not represent necessarily what the current is doing. It's just a picture of me going through all the elements in the loop so that I can add them all up. I'm going to call that just loop 1. And then I can do loop 2. So I can start right here if I want, and then we'll go all the way around this circuit as well. As you can see, the direction here does not have to match the direction of current. It's just sort of a blueprint for how I will move around the circuit, adding up the different potential changes. We need a Kirchhoff's loop law for loop 1. So Kirchhoff's loop law says that the sum of the changes in potential as we go around a closed loop has to equal 0. So that has to hold true here. So let's do 0 equals plus 1.5 volts. That is me going from here up through the battery, from negative terminal to positive terminal. Then I'm going to continue moving until I get through that first resistor. But when I get through the first resistor, according to the drawing I drew, there is a higher potential on this side than the other side, because current flows from high potential to low. So the potential at this point here must be higher than the potential at this point in order for current to flow that way. So with that in mind, I want to do a subtraction. I'll do a subtraction of the delta V across that third resistor. And that's going to be found as a product of I3 times R3. Then we're going to keep going, and we're going to move through the resistor R1. As I move through that one, I'm going again from a higher potential to lower potential. So Now, this is the higher potential than the other point. So we're going to subtract again. This time it'll be I1, R1. And at that point, we're at the same potential as we had started because we're in direct contact and there's no elements between those 2 points. So they're both at the same potential. If I assume that this point is grounded here, then we could call that a voltage of 0 volts. And that would mean that this would be at 1.5 volts, this point here. But we still don't know what the true potential is at that point. But our loop law is complete at this point. We accounted for all 3 elements. So now we want to do another loop law. This time we can go around the other little loop there. So let's start over with that. I'll start here and we'll just travel up through that first resistor. So we'll have Kirchhoff's loop law for loop 2. Alright, as I go through the current, I'm going up in potential. So we want plus I1 R1. Then we're going to go through this resistor to a new point. We're going against current yet again, so we want to add. And then for our last element here, we'll go through the battery. We're going the wrong way through the battery though, because we're going from positive terminal to negative terminal, which means we'll actually drop 4 volts. And then we're back to where we started, so the loop is complete. We can rewrite these equations as 0 equals 1.5 minus 3.5 I3 minus 1 I1. I'm just substituting in the resistance values. Over here we'll have 0 equals 1 I1 plus 4.5 I2 minus 4. And at that point, in order to enter it into an online system of equations solver, we may want to convert our variables to A, B, and C, or X, Y, and Z. I'll do A, B, and C. Alright, those are 2 equations we can plug in. As you can see though, we have 2 equations and 3 unknowns. So we have to come up with one more equation. And that's going to be a junction rule. It doesn't have to be a junction rule. You could do another loop if you do the outer loop. But we need the sum of the currents coming in to equal the sum of the currents leaving the junction. But the ones that are going in are, if this is the junction I'm talking about, I3 is coming towards it and I2 is coming towards it too. but I1 is leaving it. So this is considered an in. This is considered in, and I1 is out of the junction. So we need I2 plus I3 to equal I1. Writing that in terms of A, B, and C, it would be B plus C equals A. Go ahead and plug them into symbolab.com. This is how you spell it. I'm going to type it into Symbolab like this. You use a semicolon between equations in Symbolab. Alright, let me try it. Alright, those are my equations. It appears that I may have guessed correctly when it came to the directions of current, because I don't have any negatives in my solution. If I had guessed wrong about one of the current directions, I would get a negative. Those are my results. So I get that A is I1, and that is 0.874 amps. B is I2, which is 0.695 amps. C is I3, and that is 0.179 amps. Alright, yeah, so let's see what else the question asks, though. It wants the rate at which energy would be dissipated by the resistors. So that's taking it one step farther. Let me copy my drawing, and let's include the power now of the resistors as well. Alright, so now we know current 1 is 0.874 amps. Current 2 is 0.695 amps. Current 3 is 0.179 amps. To get the power for each resistor, we would want to just multiply the voltage drop by the current. It has this formula: power is delta V times I. So we got to find out what these voltage drops are, though, across the resistors, because we don't have that yet, so we still don't know what the voltage at this point is. So let's try to find those. To get the delta V for each resistor, let's just multiply the current times the resistance. That's using Ohm's law, delta V equals IR. So the current, 0.179, resistance, 3.5. That's a 0.626 volt drop there. So we can now subtract 1.5 minus 0.626. And now we can finally find the answer here. The voltage drop at that point must be 0.874 volts. And I got that, of course, by subtracting the 1.5 that we're at here minus the 0.626. We know the voltage at this point is going to be 0. We know the voltage at that point would be 0 too, because they're all in contact. We still got to find out the voltage at this point. Let's find the drop here for resistor 2. It's his current times his resistance. Yeah, 3.128 volts. Alright, so we know the delta V across that resistor, but interestingly, the voltage at that point, it's 4 volts, of course, because it's on the other side of the battery. You got your negative terminal at 0 volts, then your positive terminal would be at 4 volts, and since that point's in contact with the positive terminal, it's going to be at 4 volts. And it looks like that adds up. If you do 4 minus 3.128, you get to the same potential that we found earlier. And then, of course, the delta V for resistor 1 is just going to be 1 times that, which is 0.874 volts. Alright, now we know all the voltage drops across the resistors. We might want to organize this all in just a little bit of a table format. Alright, we've got all the currents listed. Yeah, let's list their voltage drops as well. So delta V1 is 0.874 volts. Delta V2 is 3.128 volts. And delta V3 is 0.626 volts. So we've got the current figured out. We've got the voltage figured out. Now what we need is the power dissipated by the resistors. Alright, so we'll use the formula. Power equals delta V times I. Multiply straight across. P1 is 0.764 watts. P2 is 2.174 watts. And P3 is 0.112 watts. Power of the cell. Okay. So to find that, we know the current going through the battery. It's going to be 0.695 for this battery. And then for this battery, it's 0.179. So you just want to multiply the voltage of the battery times the current through it. Let's do I1 times epsilon 1. That's battery 1. And over here we have battery 2. So this will be the power of battery 1. 0.179 amps. Times 1.5 volts. And for battery 2, it's going to be I2 times epsilon 2, 0.695 times 4 volts. 2.78 watts. Alright, and it should be that the sum of the power supplied by the batteries should equal the sum of the power dissipated by the resistors. That's another good check as well. So I get 3.05 watts dissipated. And if we sum these, 3.05 watts provided. Great.